Hello, everybody. My name's Sasha Ampuero, and in this walkthrough, I'll be covering my shell implementation of my.sh written in C, and I'll be demonstrating compilation, background process management, signal handling, and client message handling in the networking layer. Let's get into it. First, let's start by running make clean, which running will remove any existing object files and the binary. Now, make, compiling from source. The make file compiles each .c file individually, such as mysh.c, built-ins.c, commands.c, variables.c, and iohelpers.c, then links them into the final binary. Let's run. That's perfect. The build completes with no warnings and no errors. The compiler flags include wall, wextra, werror, as well as the full address sanitizer and ubsan suite. So any warnings would have been treated as errors and stopped the build, which we haven't found any errors, and our build's running perfectly. Now I'll demonstrate background process management. So let's start our shell. H and run sleep 100 ampersand. Perfect. Running sleep 100 in the background with ampersand, the shell immediately prints a job number and the matching PID, which aligns with Bash's conventions and the project guidelines, and control's been returned to the user right away. Now if we want run sleep 200 and we get another process starting the second background process. We type PS to list currently running background tasks. It shows both processes are running with their command names and PIDs. Now, if we type in kill 3043787, we will be using a sig term, which is the standard signal termination, killing the first process by PID. And then if we press enter once more to trigger check tasks in my shell, perfect. The shell detects that the process has finished and prints the done message, matching the format you'd expect from Bash and our guidelines. Now, once again, run kill 3043983, and then press enter once more, killing the second process and confirming we get the second done message as well. Now I'll walk through how signal handling is implemented in the code. The key requirement here is that Control C, signal interrupt, should behave differently depending on context. When the shell is waiting for input, it should not terminate the shell. But when a child process, that's including a built-in, is running, it should terminate that child and return control to the shell. So let's take a look at this signal interrupt handler. This handler, registered in the parent shell process, only does one thing, which is write a new line. This is intention. Using write here is an async signal safe, which is required inside signal handlers. What this does is it moves the new line for the terminal cursor to a clean line so the prompt redisplays correctly as you'd expect. Now, if we scroll down to main, we will find our first signal usage as a sig action. In main, we register this handler using sig action, which is preferred over signal function because its behavior is well defined across platforms. The parent shell process now catches signal interrupts without terminating. Now, if we scroll up to execute tokens, we will find another signal call. Let's talk about it. Here is the critical part. When the shell forks to execute any command, including built-ins that require a fork, the child process immediately resets the signal interrupt to its default disposition using sig default right here. This means the child will terminate on Control D as normal, while the parent handler remains in place. This gives us two behaviors we need. If you press Control D at the prompt with no command running, the parent catches it, prints a new line, and redisplays the prompt, with the shell staying alive. But if a child process is running, say a long sleep or a cat reading from standard in, passing Control D delivers a signal interrupt to the entire foreground process group, causing the child to terminate because it has a SIG default, while the parent survives due to its custom handler, which is the exact behavior we're looking for. Now, if we scroll down a little bit within execute tokens, we'll find the wait PID loop, which is one more detail worth noting. When the child is killed, the parent's wait PID call gets interrupted by the signal. Erno is set to ein ter. The loop tries wait PID until the child is fully reaped or killed. Without this, the parent could lose track of the child and leave a zombie, which is exactly what we have to be careful for within this project. Now, if we scroll back up to check tasks over here, we can talk about our done messaging. For background processes, done messages are generated by polling with no hang on every prompt cycle. No SIGChild handler is needed, which we'll discuss later. No hang lets wait PID return immediately if the child hasn't finished yet, so it doesn't block the shell. Both whiff exited and whiff signaled are checked, so a killed process also triggers a done message. Now, I mentioned it earlier, but let's discuss an alternative. In terms of design alternatives, a common alternative is to use a SIGChild handler when a child exits. The kernel sends SIGChild to the parent. You could handle done messages inside the signal handler or set a flag that the main loop checks. The reason I didn't go for such a route is that the SIGChild handler introduces complexity about re-entrancy and signal masking, especially when you have multiple background children. You would need to loop inside the handler, calling wait PID until it returns 0, and you need to be careful about which global state logic you use inside the handler, which I found to be overly complex. This polling approach is far simpler, predictable, and doesn't require async signal safe restrictions on the done message logic, which I felt worked a lot better within my project. Lastly, I want to walk through how the server handles incoming messages from clients, with a focus on how very long messages are dealt with. So let's navigate to builtins.c. Here, right here, each connected client has its own 256 byte receive buffer and in-buff counter, tracking how many bytes are currently in it. This is important as the TCP is a stream protocol, so a single read call might return a partial message or multiple messages at once. The buffer exists to accumulate bytes until we have a completed message. Now let's scroll up to read from socket right here. This is a key function for reading from a client and is something we actually ported over from our lab because of its usage, especially within servers. It reads into the buffer, starting at the current fill position, buff plus inbuff, and reads at most buff size minus inbuff bytes, so it never overflows the buffer. The first line here is a hard guard, which means if the buffer is already full and we still haven't seen a complete message, we'll return -1 immediately, which the caller treats as a disconnect, which is handled appropriately, which this error call is handled appropriately within my shell. Now let's navigate down to the meat and potatoes and run server get message. Usage of get message right here. This is a long loop within a long function. And get message looks for the network new line, which includes carriage return and line feed that marks the end of a message. When found, it mallocs a copy of just the message and shifts any remaining bytes to the front of the buffer. The while loop handles the case where multiple complete messages arrived in one read. Now, for the long message handling, there are actually 2 enforcement points on the client side before sending. The client checks the message length and refuses to send anything at or over 128 characters, printing an error message to the user instead. On the server side, even if a long message somehow arrives, say from a third-party client that doesn't enforce the limit, the server truncates at byte 127 which is found right here, by writing a null terminator before processing the message. This this is a simple approach to a complex problem that shouldn't really arise unless people have malicious intentions of abusing our product. Now onto the pros and cons for implementation. The pros are that it's simple and safe. There's no dynamic allocation for buffering partial long messages, and the buffer is a fixed size, and the oversize check is O1, which is extremely fast. The client-side check gives the user immediate feedback by providing a response, and the server-side truncation ensures that the system never crashes or misbehaves, even with non-conforming senders. The main con of this approach is that the server-side truncation is silent. The sender gets no error message back from the server, and the message itself is delivered truncated rather than rejected. For the future, a more robust design might send an error response back to the client before discarding the message. Additionally, because the buffer is only 256 bytes, which can be found here, which we discussed earlier, if a client sends a message longer than 256 bytes without a new line character, which is something a malicious or buggy client could do, the buffer will fill up and the client gets disconnected rather than getting a meaningful error. For this application, it's acceptable, but it's something worth noting and to be fixed in the future. All right, that covers compilation, background process management, signal handling, and client message handling. Thank you for watching and all the best.